Everybody kind of went
Good afternoon,
quiet.
everyone. Welcome to our webinar. My name is David Gowu from the Institute of ICT Professionals, Ghana. Today's webinar is about the low-cost ventilator that's been developed by Professor Fred Magbaganlore and the team from Academic City University College. We are here to go through the entire process of developing this wonderful ventilator, and we're looking forward to a very exciting and engaging webinar. Welcome on board, Dr. Fred.
Thank you.
Yes, please take it from there. Thank you.
All right. Thank you, David, and IIP for putting this webinar together. I appreciate your time as usual and the effort you guys actually bring to bear in trying to sanitize our IT delivery processes in Ghana and to be a strong advocate for the profession. So thank you so much.
Thank you for your support.
For everyone online, thank you and welcome. Today is actually my first online webinar, so
great. We are happy to be the ones organizing it.
You can make a check mark. So anyway, this whole idea of a ventilator, I mean, would never have happened if we did not experience the euphoria of the impending lockdown the president was about to announce. And there was just a certain feeling of insecurity, fear, uncertainty, and naturally, we all gravitate towards prayers in times of such uncertainties. And, you know, I just thought 16 years of medical devices experience, and as an engineer by training, we tend to look for solutions differently. I personally think that divine inspiration comes through into solutions, and that prayers alone are not sufficient. Prayers without action are not sufficient. So a typical scientist view of life. So anyway, I basically sent an email on Facebook, a short message on Facebook saying, hey, are there other people there that potentially could be home and bored? And would they like to try their hands on a product development process that could help solve or alleviate the pandemic? And I got over 120 responses from all over the world, Ghanaians, non-Ghanaians, people equally anxious to try to make a contribution. And you know, my hope is that other people will see the videos, other people will see the efforts that we are making and start believing that we can actually develop products and that these things are not some mysterious stuff that came from Mars. And we shouldn't be afraid with the nice packaging that these products come in. So without further ado, I brought a team together and we started brainstorming, and some of the stuff that I'll show you here today is basically the outcome. So I thought a presentation like this would be useful if we could actually examine what the anatomy of respiration really is. Why do we need ventilators? And then we'll look at an overview of a ventilator. Then we'll then delve into what we did and where things stand today. So, you know, every one of us on this conference today is breathing. We breathe in and we breathe out. When we were kids in school, they will ask you to sit a certain way, put your hands on the table, breathe in, breathe out, breathe in and hold for a while and let it go. Now, if you can do that, you are very fortunate. If you can do that, you're very fortunate. You're one of the fortunate few who doesn't have any acute respiratory problems. If you can't do that, then you're a candidate for a ventilator. And then oftentimes there's a confusion between what a respirator is and what a ventilator is. I just like to say a respirator is a specialized form of a ventilator. There's a lot of noise in my background, so if you can hold on for 1 minute, I'll stop this.
Okay. All right, for those who just joined us, this is the webinar on the low-cost ventilator being delivered by Professor Fred Magbagan-Lowry from Academic City College. Professor Fred Magbagan-Lowry is the president of Academic City College, University College that is in Hachu. He and his team developed a low-cost ventilator to combat the coronavirus pandemic. So this webinar is to help us to understand the process of developing this low-cost ventilator. Okay.
So what was the situation? When we started this a couple of days later, the government confirmed 9 cases of coronavirus. Well, right now we have about 5,000 plus. So it is still a situation that is evolving very fast. And at the time we started this, our understanding was that there were only 67 ventilators in the whole country. Further investigation showed that that was really true, but we had a lot of them that were equally broken down. So we have dual challenges now. Not only are we supposed to innovate new solutions, but we at minimum have to have the skill sets to fix the one that we import into the country. Okay? So look, if you walk into a room and you say this place is too stuffy, or you tell somebody, can you open the window, it's too hot in here. Give me a fan or papa, as we say it. The freezer is producing a lot of heat and you can actually experience it when you go behind it. When you travel an afternoon, you know, all these experiences tell us that they are venting, they are trying to respirate, they are trying to feel comfortable. So there is an element of comfort in experiencing the ventilator. Okay. So you can now imagine internally when you've gone through surgery and you cannot breathe, or you have acute lung problems and you are unable to breathe on your own. Somebody has to open that door for you. Somebody has to bring that papa for you, to fund you. And that is where a ventilator actually comes into the continuum of care. It is an assistive device that when you can't breathe on your own, it helps you to breathe. Now, if you look at the anatomy of respiration, it's really, really complex. I mean, look at the beauty of the picture that is on the screen right now. And all these different organs that are actually involved in the respiratory process. And so to try to design a mechanical device to support the biological system is a challenge. And this challenge manifests in the complexity of the ventilators that we see in hospitals. All the whistles and bells, the alarm systems, the valves, are to ensure that those systems, once in the patient, are actually supporting life. In the event that aspects of those do not work, then death becomes imminent. So if you look at our respiratory system, as I indicated earlier, it has a lot of organs and parts of the body involved in it. And the sole purpose of this is to exchange oxygen and carbon dioxide. So a ventilator also helps with the oxygenation process and also helps us to expire the carbon dioxide that our body is producing. So in an ideal situation, you should be able to get a controlled dose of oxygen, and then you should be able to maximize the expelling carbon dioxide from the body. Look at the parts that are involved. Everything starting from your nose, all the way to those invisible capillaries that surround what we call the alveoli, that are actually where the exchange of oxygen and carbon dioxide occurs. Okay. So I wouldn't read through all this, but you know, the whole process starts when you inhale, and then it ends when you exhale. Okay. So if the lungs cannot perform that function, something else have to do it. Now, at the cell level, you really have these beautiful things that look like grapes over there, surrounded by your capillaries. And those are actually the guys that coronavirus is known to attack. And when these alveoli either collapse, have collapsed, then you have these acute respiratory problems that a ventilator essentially needs to come in, like your tire pump, to inflict the ones that have already collapsed, to keep the ones that haven't collapsed yet, and then the ones that are half filled to return them to normal. There are 600 million of these alveoli in our bodies. Okay. So what does a typical ventilator look like? I mean, in the last 6 months, I've seen different configurations of them, but typically what you see in the hospital is something that looks like this on wheels, and it has a screen that shows pressure, flow rate, and you know, the nurses will set up all the parameters, and then they have an interface to the patient, and then of course, oftentimes in the ICU, most of them are connected to oxygen sources. So essentially, from a mechanical engineer's perspective, the ventilator has 3 key parts, what I call the air compressor system and the oxygen system, essentially the source of that oxygenation air. And then you have the patient interface, which is all the tubes that go down into the trachea. And then you have the controls, which is basically the electronics that controls the flow and keeps the patient comfortable. And as all the alarm systems that are activated when parameters exceed certain preset conditions. Okay. Now, most of the ones that we see today in the hospitals are what we call the pressure, positive pressure ventilators, when air is actually delivered directly into the patient's lungs. There used to be what we call the negative pressure. You can hardly see them now. They were mostly, they look more like caskets where polio patients who had lost function of their muscles were put into these cages and then artificially compressed to be able to breathe. We don't see those anymore because the technology has evolved significantly. So our focus is completely on this positive pressure ventilation system. Now, when you look at a typical ventilator in the hospital, the number of parameters that you need to set are tremendous. You have this IE, you see the ratio of the duration of inspiration versus expiration. Of course, if the expiration piece is high, as you can see over here, 1:2 is about normal. So it means you're spending more time expiring, removing more carbon dioxide from your body stream. So part of the complexity you see is trying to manage all these parameters. So I'll tell you upfront that most of these parameters were beyond the scope of the low-cost ventilator that we attempted to design. Okay. The other thing you see quite often is a technical specification sheet that comes in like looking like that. You know, the tidal volume, you have the respiration rate. Some of this we would address in the system that we have designed. Okay. So let me step back here. Now, often you also hear about modes of operation. whether the ventilator is pressure controlled or is volume controlled, or whether it's dual control systems. Again, the system that we have can operate in both modes. So now, what did we do, really? We tried to find, since everything was closed out, the country was shut down on a Monday, I believe, and we only had a Saturday to figure out what we could buy for our project. And so we had a short schematic, as you can see, that you need a compressor. You need to compress air, deliver what they call the medical air, which is about 21% oxygen. And then you need to be able to couple it up with an oxygen source. And then you need to be able to deliver this to the patient. But in between the patient and your air generation sources, you have controls. You need to control them. If you overflood the patient with air, you are going to kill them. If the patient wasn't breathing and you started giving them ventilator air, and all of a sudden they start breathing, the system has to be able to detect that the patient is beginning to exhibit some breathing activity, so that you don't continue to push air in when they are trying to push air out. You will kill them, okay? So that is where some of the complexity in the systems we see in the hospitals are. In many parts of the world, if you put a patient on a system like that and they get killed, you will be sued for that, as there are strong liability issues associated with those. And so you see this complexity. Also, if you look at the new generation of ventilators that came into the market as a result of coronavirus, there is always a disclaimer that says, you know, these are emergency systems. You can put it on patient as long as the patient signs that it is okay to put it to them, because they don't have all the whistles and bells that you see in the commercially available, but now unavailable ventilators. So how did we start? We locked ourselves up in a room, a bunch of students, some professionals from the medical devices sales side, and we tried to understand the biology of what coronavirus actually does to the lungs. So this is the first initial sketch. So you will see the lungs up there with the bronchioles. And we've isolated an alveoli that looks like it is okay. So we don't have to worry about feeding it with oxygen. You have one that is partially filled, and you have the collapsed one that looks like sickle cells, okay? So the job of the ventilator is to be able to restore all this to normal and to help the patient take over breathing by themselves. Okay. So now the question is, how does a typical ventilator work? As I indicated earlier in the schematic, you need your air source, right? If you're not in an ICU environment where there is no oxygen, then all you have is your air compressor system that can deliver an air quality of about 21% oxygen, okay? So we need a compressed air source, which is slightly indicated here. You see it come out better in the schematics. And that should be able to generate anywhere from 200 milliliters to about 1,000 milliliters or a liter. And you need to find a way to ensure that that air is moist. Because oftentimes even with normal lungs, when we breathe in dry air, you cough, okay? So this air goes from your compressor source to a humidifier that has water in it. And that is where you moisturize the air. And then from the lungs, from the humidifier, you deliver the moisturized air to the lungs, okay? And there's a one-way valve here because you don't want anything going out and coming back into the humidifier. And then when the patient exhales, okay, this route here, you have scrubber. And the scrubber is actually a pressure device that ensures that all the alveoli that have been inflated do not collapse when you exhale, okay? So it maintains pressure slightly higher than the prevailing atmospheric pressure so that the inflated alveoli stay normal. And then, of course, we also have a one-way valve here to prevent whatever air you exhale from going back into the lungs. And then from the PEEP, we deliver the expirated air into what we call a scrubber. And a scrubber is basically a trash can, okay, that has some chemicals in it, maybe alcohol, 80% ethanol content. And it's supposed to kill any viruses or bacteria that you may have expired. And then once those are killed, the residual air escapes into the atmosphere. Okay? So again, conceptually, we're trying to get the biology of the problem that we're out to solve, and then obviously the underlying physics and chemistry. So this is a typical problem where you have all your basic sciences at play. Okay. So more sketches, similarly, in the product development, you start from something that looks wacky, and then you start refining it. So again, we have your external pressure source here. In this case, we had a cam that is pressing on an ambi bag, and the water is going into the humidifier, then to the patient, then to the PEEP, and then out from the PEEP into the scrubber. So now, you know, a student jumps up and says, I can take that sketch and make it look nice. Okay? So again, we have an air pumping source into your ambi bag. In this case, you have a one-way valve, delivers it into the humidifier, into the lungs, out into the PEEP, and out into the scrubber. So the ideation process is beginning to be refined, it's beginning to look professional. Okay? And so you have the inhalation piece on this side, and then the exhalation part on this side. Now, in this simplicity, this schematic also captures the spirit of the ventilators that are in the market today. Now, they may not have a big humidifier container here, or the PEEP may not look the way it is here. It may be just a small adjustable one with filters. But the physics of it is essentially captured in this presentation. Okay, so now we understand the biology here, what we're trying to solve. We understand the physics of how we're going to generate compressed air. At this point, we're not even talking how oxygen comes into play, because the oxygen system is a standard system that you can basically just connect to this system. So we're entirely looking at a product that you could actually take into a remote area, and if you have any source of power, you'll be able to run it entirely without worrying about an oxygen tank. Okay. But as we go, you will see where we begin to couple these together. Okay. So now, we're now beginning to think, remember in my initial schematic, I said we are looking at three parts here. You have the air source, you have the patient interface, and then you have the controls. That's what ties the two systems together. So our initial focus was, what are mechanisms that we can design to be able to deliver compressed air? Okay. How do you deliver compressed air? One of the examples you will see is we simply use a technology that blacksmiths have been using forever, which is producing air by compressing leather bags as bellows. So we explored that possibility. In fact, that was the first model that we designed, because we could get leather and we could get wood, and we were able to design that the very first day that we met. Now we started getting ambitious also. So if you look on my screen, you'll see typical reciprocating displacement pumps. If you look at A, essentially you have the plunger rod all the way at the bottom of your well, and when you lift it up, whatever mechanism you have, you get water coming out. Okay. Then if you look at B, you have your well all the way down, and then you have atmospheric pressure acting on the surface of the water. So if this is a vacuum here, as you pull this plunger rod up, you suck water with you, and you can deliver this in your borehole. Now, the one that was interesting for us is this piece here. Let's see if I can move this away. Okay. So here you have an enclosed container here, and then you have water. So theoretically, depending on how far you push this plunger down, you will displace an equal volume of water, which is what you see here with these arrows. Okay? So the water will come out of here. But if you can control this water level here, then when you push this in, the water will rise. But because this displacement is controlled, the water will not rise too far to come out of this spout. Instead, air will come out. So the physics you need to figure out now is what this water level ought to be, how long should this plunger rod be, how far should you push it down so that you're not getting water into the patient's lungs, but you're getting air. Okay. So that here was the initial sketch. And all we had available was PVC pipes. And so the interesting thing is that the first time in attempting to find out what the optimal level of this water should be, we got a lot of water going into patient tubing until we figured out the optimum. The additional challenge we had was that because these were non-transparent PVC pipes, it was always hard to gauge what the water level is. So in a real product, this would be a transparent, either polypropylene or polycarbonate plastic with graduation on it, so that you can always tell what the optimum water level needs to be so that you can only displace air. So let's keep going. So now we were confident that we had a mechanism that would generate air for us. We understood from the schematic the workflow. So now we started looking at what happens in practice when these systems are in an ICU. So in an ICU setting, you just don't have the medical air, which has only 21% oxygen, but you also have an oxygen tank. You need to be able to set the pressure levels for your oxygen, your pressure level for your medical air. And of course, you need to have alarm systems on them so that in the event that you exceed your set thresholds, the alarms will remind you to that, remind you about that. Now, and also there's a sensor that measures the quality of the oxygen. So in your commercial ventilators, if the quality of the oxygen doesn't reach a certain threshold, an alarm will sound. And then of course, you need to mix the two up in your gas mixer. So you will find this in the hospital, okay? And then once you mix them in their proportion, you have this FiO2 device that basically tells you the composition of the mixture. And I think it's anywhere from 21% to about 100%. Now, what the patient gets, the optimal setup depends on the doctor, depends on the patient, depends on the patient's age, depends on the level of their ailment. And that is outside the controls of an engineer. It's in the hands of the caregiver. So in some setups, the oxygen already goes through a humidifier before it goes to the FiO2. In our setup, we're looking at the gas after it's been mixed, going into the humidifier, and then going out into the exit directional valve here. And then the clinician can actually control the flow to the patient. Okay. And then, as you saw earlier, from the patient, it goes into the PEEP. And of course, if the PEEP pressure drops to below a certain threshold, you need to be alarmed also. You need an alarm. And then you get into the scrubber. Now, the biggest challenge we had, of course, was trying to get a sensor. And the purpose of this sensor here is that as you flap these patients whose lungs are not functioning, either completely or partially, at a certain point, they will start breathing. And you need to be able to detect that breathing activity so that you are not going in one direction while the patient is going in the opposite direction. Okay. We ended up harvesting this from some old therapy surfaces that I had. and the kids were able to actually make it work with the syringe. Okay? So now that we've gone through the prototyping phase, we are able to get the real sensors to do that. So you will also see that in a typical care environment, you have all these displays, you know, showing you the status of all the valves, the flow rates, the pressure, the volume that is being delivered. Again, in our development, this is really where we are now, because getting the parts in the shutdown was a big challenge for us. Okay. So what I'm going to do next is to go through a few prototypes that we started looking at. So you saw this one from the reciprocating pump. You have the container, you have water at a certain level, and you push the water down. If it has no exit, that water is going to push the air above. And that is how this initial prototype was designed. And the control is basically a rack and pinion systems. Okay. So basically taking a rotatory motion and translating it into a linear motion. So you see Celon there. Celon loved this model to death. See Barnabas there, one of our students. So the challenge here for the students was that we were testing this using car batteries and ended up killing our car batteries and the batteries that we had. And so every day we have to take them out for charging. And the students were able to design their own step down. So essentially we take 240 volts and drop it down to about 15.5 volts. And basically that is what is going to be packaged into the final system. So that was the first prototype that we had. Now, if you look at this prototype, it really takes a lot of space. You look at the length of that PVC pipe. Controlling it was challenging also because we couldn't find V-slots, we couldn't find linear motion guards, everything had shut down. And so we started thinking slightly different. Could we divide that into two? You know? So I just took this picture today. So this is basically a piston action, and you can actually miniaturize this significantly because all you really need to ensure is that you are getting your 200 milliliters to about 1,000 milliliters or 1 liter. And so if you can deliver that into the system with minimum footprint, that makes packaging easier, transportation easier as well. So this is a prototype that we're looking at. Then there was a prototype that actually went viral. It's called a MacGyver ventilator. So you will see all you need is that slapping handle, a PVC pipe, and that ambi bag. Okay. So let's see how this works.
You see us handle in the PVC pipe pushes on the ambi bag and you get air coming out. So this casing is completely made from wood.
As you can see, we're delivering enough air into that green bag, which is the lungs, represent the lungs in this case.
So this is where we're going to have our humidifier and scrubber and the pip. And this we can modify significantly based on available technologies. We can have an adjustable pip, so we don't have to have a whole container.
So now, from the last schematic, this is where the oxygen comes in. So you see a humidifier here, and you have your oxygen line that basically connects to the ambi bag in this configuration. So again, one thing you have to keep in mind is that the patient circuit varies significantly. In this case, you have the humidifier right here attached to the oxygen tank. And so it's already humidified by the time it meets the medical air in the ambi bag. So you see the oxygen is connected. So what we are pushing here now is the oxygen and the medical air combined directly into the lungs. Now, so your PIP is actually what prevents this thing from going back to being flat completely after the patient breathes out.
Students are working on the controls, as you can see, and as a standard, it's all wires right now. Once we are done assembling all this nicely to drive the motor, monitor the pressure, and the stamina of the patient, all that stuff is going to be integrated into this. And all the alarms, the beeps, will all be codified. And that box was sent somewhere in Wellington. So you see, we are just a few steps away from.
Doc, the volume is very low, so maybe you need to explain again the video.
All right, so here we've integrated the oxygen tank directly into the ambi bag, and then we're just using that tiny handle to push it. In fact, one of the doctors that came from Kolegu said, I can use this, I can just take this and use it there. You know? So without the whistles and bells, without all these alarm systems, we basically have a basic system that can deliver air into a patient that needs it. Of course, with medical supervision. The next obvious step is to make sure that we've integrated minimum controls to make it possible for this to be used. Let's see what this is. So, and this is made of wood. I mean, the casing is completely wood. The motor there is your typical windshield wiper motor. Let's move on to the next. So let's look. Sorry. So this was our original design, and I tell you, it's gone through so many. Gone through multiple iterations. So you almost cannot hear anything. I mean, this thing is pushing almost 1 liter of air out. Okay? And that's your windshield wiper. We didn't invent that. And then again, you know, when you take a look at a Lamborghini, it looks really beautiful outside, but when you take the top off, it's nothing but chassis, you know. So what you're looking at here is not sexy yet until we really package it and make it look nice. But this is what is underneath the chassis right now. Okay. So, I mean, most of this basic work was done within the first 2 weeks. If you look at the original videos for this particular one, it was very complicated with multiple moving parts, really, really loud. But as we got very comfortable with the design, we got it to a point where we say we can design this for manufacturing. Okay. Now, don't forget that I'm sitting down here presenting this, but most of this work was done by second-year engineering students. Second year, not third year, second-year engineering students. And so part of the product development process also involved coaching. And what I'm showing you here is the typical, typical day at 2 o'clock. We assemble everybody together, and then we try to converge everybody on where we stand, what the challenges are, what we need to do the next day, and then they get opportunity to ask questions on product development. So let me just play this. So this is our workshop. You can see a wind tunnel behind. So this is our Dean of Engineering, Lucy Ajipon, who was managing this project. And we are practicing some social distancing, you know.
Okay, so the team here is debriefing, catching up to see where we are, where the challenges have been so far today, what the next steps ought to be. So we're actually behaving like a real engineering team, which we are, right, guys? IT real engineers. Okay.
Okay. So, you know, in short, within 4 weeks, we were able to basically develop 5 prototypes, 2 definitely from viral videos, which is the MacGyver model and the one from MIT. We had a lot of support from 3D printing companies. We had a lot of support from people who were bringing the students lunch or sending us Momo to buy lunch for the team. At the time, nobody could travel. The Minister for Environment, Science and Technology gave us a letter so we could drive around and pick people to their shops in La Paz to open their shops and sell us motos. We could go to people at Agbogloshi and drive them to their shops so that we could get parts to buy. And so this was done at a time when there were no movements. And we actually drove all the way to Koforidia to bring one of our students, Barnabas, who was our electronics expert. We attempted to go to the north to bring another student who was very, very good with power systems design. And then we found him in Kwabenyang. And so this is for me to have provided guidance for these students and just to watch second-year students do what these guys were able to do in a very, very short time gives me a lot of hope. And every single one of these devices have gone through, so if you look at the initial slide that I had put up, you know, ideation was very, very brief. It was almost a military-style product development. We had some volunteers in the US who were investigating procurements, wherever they could find procurement stuff. Some were volunteering to do 3D modeling for us. And we basically just jumped into development. And then halfway through this, we brought a team from Kolebu. We brought 5 doctors from Kolebu. Because one good way to design a medical product is to make sure that your stakeholders are involved. And the earlier you have them in, the better. You know, so they came in and they looked at each prototype, gave us the pros and cons. The one that was functioning at the prototype level was the what we call the modified MacGyver model. And one of the doctors said, look, if you are in an ambulance today, and somebody is really, really ill, instead of sitting in there and squeezing an ambu bag, I could turn this on and then I can proceed to put in an IV on them. So I can use this today. And then they invited the team back to Kolebu to show us the traditional ventilators that they had. And that also informed what our footprints would look like, basically the form part of this product development. And of course, they gave us a long list of other things that they would like us to do for them once we go through finishing up our ventilator project. So essentially where we are now, if you look at the 3-part system, which is basically the patient interface, that is off the shelf. You can buy all that stuff off the shelf. If you look at the air compression system, I think all the models that you've seen so far can generate air. If you look at the control systems, basically driving the motors, making sure that the thresholds are set correctly, making sure that patient is in stable state and that you have a system that monitors them. That is really where we are right now. And I said, our prototype seems good. The challenge is trying to source these parts from Alibaba and the US has been a little challenging. Our plan is that by the end of this month, we should be able to, and by the way, we also brought Ghana Standards Authority. We brought the Director General in to come see what we're doing. So our plan is to be able to give one system to Kolebu and one system to GSA. And you know, what is quite interesting is that even we can create our forms around cane baskets. We can use bamboos to enclose this stuff. Because one of the things that I actually didn't mention in all the tubing is that you actually have filters. You know, you have filters to make sure that the air that is getting into the patient has high quality. And so if you have filters in your system, then your enclosure should not be some expensive aluminum formed or some expensive plastic. We can actually use local material, just like we use the ladder, to make sure that you have a system that can at least sustain life. All right, so this is just a broad general overview. I've kept the physics to minimum, but if you have any questions, I'll be happy to address them.
Thank you very, very much, Dr. Fred. I think this has given us better insight into what the team has been working on. My first contribution is the other time we realized that you wanted to raise some funds, but do we have a local option of, you know, donating via Momo?
David, you broke off. You said my first question, and then you died off.
Yeah. Actually, no, it's you know, about 2 weeks ago, you put out some you know, requests for funding for some parts of the things that you are working on. And you indicated that, I mean, I saw it, but then we don't have the local option of, do we have the local option of donating via Momo?
Yes, we have Momo. One of the students have Momo that we use.
Okay. So what we may look at is to create a platform where people can actually come and apart from the one you have, so that we can also integrate our local mobile money setup on it. So that
was the president of Ghana. Yeah, so we have Momo. Dr. Kwame Boakye just signed a check for $2,000 for us. So
great.
that is terrific.
Great.
Dr. Kwame Boakye used to be Chief Operating Officer for Harrison Corporation in the US, and he was also president of Ghana Institution of Engineers.
Right.
So I would say we've received a lot of support from Ghana Institution of Engineering. They are just excited that something is going on locally.
Fantastic.
We had a widow, not a widow, a retiree, Madam Stella Edu, who wrote a check for 3,000 CDs for us. And she's committed another 7,000 when we get to a pre-pilot version. So, you know, we've received so much. I mean, no amount is small. My classmates from the US committed to donating $50 each just to keep the process going. So we've received, you know, 20 CDs from people, 10 CDs to buy lunch just to keep the students going at a time when there was nowhere to go eat. We just contract folks to just bring them food.
Okay, since there is a Momo option, we'll also be sending our widow's mite soon.
Oh, thank you.
We look forward to other support from other people.
Yeah.
Now, you mentioned that there are some other things that you need support, or can you elaborate those things again so that we know?
Okay.
Maybe there will be something that can come out from the platform.
Yeah. So right now where we are is buying the electronic components. You know, so you need a flow meter, for instance, to make sure that the caregiver can control the amount of air that is going into the patient. This is an off-the-shelf system. You could also control that with a solenoid valve. In one of the schematics, we saw the gas mixer. You need to be able to mix the oxygen and the medical air, and then be able to check the quality of it. That's off-the-shelf device that we need to buy. Then we need to control, we need a step down. We need to buy components that helps us reduce the 240 volts or 110 volts into something that electronic systems can manage, 12 volts, 15 volts. So just the basic components, the filters, if we are to give one to Ghana Standard Authority and Korle Bu, it would be nice to give them a complete system with a patient interface. Again, all the tubings that go into the patient are all off the shelf that we need to buy. So those are really, and then of course the packaging.
Right. The packaging is one of the key areas,
exactly.
and I know it will require
like
a bit
I said, you know, you can have a Lamborghini, but if you don't package it nicely, it will not look appealing.
Yeah.
So those are some basic things that we need help for. And then, of course, when you have 4 or 5 students working and they're not being paid, a little bit of lunch is one way to keep them going. And
right.
I mean, most of it, I footed that myself.
So we need to
any help will be useful.
Very good. So the floor is open now. If you want to ask a question, please raise your hand. There's an option there on the Zoom that you can raise your hand, and then we can just allow you unmute, and then you ask, and then we can get some feedback from Dr. Fred. Yes, Mark Fuller, please go ahead.
Hi, I'm Mark Fuller from Northeastern. We actually are working on passive breathing assist devices and have 5 being tested at Korle Bu Hospital. Hopefully it prevents a few patients from ever needing a ventilator. My question or concern is we have a similar problem to you of scrubbing the exhalation air. I think just bubbling through ethanol may not be a good solution because most of the virus are in the center of the bubble. We're looking at putting a cloth, say, soaked in ethanol that the air has to go through after it's bubbled. So just your thoughts. Have you looked any further into scrubbing the air that's being exhaled? Thank you.
Okay, so let me answer that. That was one of the areas that we debated on for a while. And one of the students just went into a lab and brought a hot water heater. And he said, well, can we make our scrubber out of aluminum, and then we put a heating coil at the bottom? So basically roasting whatever goes in at high temperatures. That's about all we've really thought about, but the issue of how dangerous this virus is being let into the air and whether ethanol was enough was of great concern to us. So we are thinking about a heating filament or a heating scrubber. And
so basically to ensure that the air that is coming out from the patient is not reinfecting other people, isn't it?
That's correct, yes.
Right. Okay,
and whether the alcohol, which is what I said in my presentation, whether the alcohol that this virus is coming in, it's sufficient to kill it. And how do we guarantee that the air that eventually escapes into the atmosphere doesn't have, you know, live viruses in it?
Right.
For lack of a better word.
Right. Okay, so, we have Nyonyo Please, Nyonyo, please unmute and ask your question.
Yes. Doc, thank you very much for the presentation. I came in late, so probably if portions of my questions or question has already been addressed, then I'm really sorry. I didn't follow from the beginning.
No problem. Okay.
So this is the thing. Later into the life cycle of this COVID thing, we are now hearing that the ventilators are actually killing patients faster than they probably if they were not put on the ventilator at all, because initially the impression was that COVID-19 was a lung disease. I mean, it attacked the lungs, but apparently some doctors are saying that it is not the case. It's actually the blood, but we thought it was the lungs because the lung was now trying to fight whatever the problem was. So, I mean, how does all of this come to play? How does it play out in the end? Yeah.
Yes, so that's a fair question. I've also seen a couple of videos that have gone viral in this discussion. My attitude to those have been twofold. The first is that a ventilator by itself is an integral part of the continuum of care. So even in the absence of the coronavirus, our hospitals, especially in the developing world, lack them. We don't have them, whether for emergency or for normal hospital operations. The president just announced that we're going to build 88 more hospitals. All those hospitals are going to need ventilators because they come in handy when people cannot breathe because they have acute pulmonary illness or they've gone through surgery and they cannot breathe entirely on their own. So the first answer is that they are needed with or without the coronavirus.
Yes, yes.
So that is one. The second is that coronavirus has become the blind man that went to see the elephant. Madagascar thinks they have the right potion. The world thinks they are clowning. Nobody really knows for sure yet. If we do, people will stop dying.
That's right.
Like I said, when we started this project, there were only 9 cases reported in Ghana. Yesterday, when I checked, it was 5,127. And we also know that this virus is evolving. It's mutating at an alarming rate. So I think for now, the need for a low-cost ventilator in our part of the world is still a worthwhile effort. And we need to innovate, It is sad that we are still buying syringes and we are still buying needles. And when you go to Korle Bu, you see the frustrations that the doctors themselves have when they need a simple device and it needs to be imported for $900. And so part of my effort is how do you also excite a new ecosystem where innovation is demystified and people can actually go out there and try things and make them work, because the only way you innovate is by trying. So that's a long answer to a short question.
Yes, I also agree. I think if we don't get anything from COVID-19, we should be able to now ignite some kind of new awakening in the area of innovation. The next person is Louisa. Louisa, please unmute and ask your question.
Okay. Hello, Doc.
Hey.
That is really awesome. Congrats to you and the students and everybody involved. So my question is on the alarm systems.
Yes.
What I want to understand is, so for example, there's an alarm system that checks the quality of the oxygen, as well as other alarm systems in the whole product. How does a system work with regards to the reaction to whatever the alarm sounds on? So for example, oxygen quality is bad, alarm goes off. Is there some internal mechanism that acts on it?
Oh, you mean when the alarm goes off, what happens?
Yes, yeah.
Okay. So I'll tell you a recent story that I heard. There was Korle Bu now actually produces its own oxygen. And a couple of months ago, all the ventilators started beeping, apparently because the quality of the oxygen that was coming up wasn't, I believe, up to 80%, and I'm guessing right now that number. And so all the alarms were essentially beeping. Okay, so when the alarm, the oxygen quality doesn't reach the threshold for patient care, like I said, the typical medical air is about 21%, and you need to add oxygen to it. And that FiO2 has a range of 21 to about 100%. So depending on the level of oxygen the patient needs, which is what the doctor determines, because excessive oxygen can also kill the patient. So it's not really the engineer who decides what that threshold number is the caregiver. And so if the quality, if your room temperature oxygen quality is better than what is coming from your oxygen system, that alarm is going to get triggered. And when it gets triggered, they have to shut off the machine and get quality oxygen. And in the case of Korle Bu, that's exactly what they did. They shut down their system and ordered new oxygen tanks from Equip, which is apparently one of the major oxygen distributors in Ghana today. So those alarms just don't go off and nothing is done. Something has to be done. If your PEEP alarm begins to go off, it tells you that the patient is not retaining enough air in their lungs to keep their alveoli inflated. And so you need to go check whether they are actually alive. You know, so those alarms have responses to them. It's almost like a patient ringing a bell and a nurse having to go respond to find out exactly what the patient needs. So there are corrective measures that doctors put in place when those alarms go off. Makes sense?
Thank you very much. And you're coming back again for another question. Right. Yes, Nyonyo.
Yes, thank you.
Just to add to that, you know, if you look at most of these COVID-related ventilators that are being designed, they are mostly straight down, you know. I saw a few online where you actually have to sign a disclaimer. And if you really say it's low cost, you can't have all those whistles and bells, you know. So what we would do when we package our electronics is perhaps to make sure that when the patient begins to breathe, there's a sensor that detects that the patient is breathing, and then corrective measures are taken to control the flow rate to them. That will be a baseline ventilator that you can sell in an emergency situation. Because by the time you finish adding all those whistles and bells, it's no longer going to be a 5,000 CD ventilator. It's going to be a $70,000 ventilator.
Yeah, yeah. So the packaging makes it more expensive.
Yeah.
Eugene, yes, you want to ask a question again?
Sure.
Yes, please, Doc.
Yes, sir.
Have you considered miniaturization of, you know, the ventilators, whereby it will be possible for individuals to actually, you know, own their own ventilators, you know, rather than this reuse thing, you know, because the risk of reinfection, yes, we might be disinfecting them and all of that, but sometimes, you know, the chances that, you know, there'll be slippage, you know, the virus to some other parts or components of the ventilator, there's that possibility.
Mm-hmm.
So some people might be willing to afford their own ventilators, and if it's small enough, yes, why not? So I don't know. Is it possible, looking at the components that go into the manufacture or production of the ventilators?
Mm-hmm. Mm-hmm. So, you know, obviously, as an innovator, I never say anything is not possible. The day I say that is the day I die. even if you look at the stuff, look, our intention is to have ventilators at home just like you have fire extinguishers.
Wow.
That's really the intention.
That's great.
And everything we've shown you so far, I keep emphasizing the word prototype. And only product development guys do that. We were never making any exorbitant claims. We're just saying that we have concepts. We went through an ideation process, developed concepts, we've developed prototypes. Now we are getting to a point where we are going to start turning those prototypes into products. Now, having said that, nothing stops us in an emergency situation for somebody to say, okay, I'm going to sign a waiver to put a prototype on my mother. You can do that. You can do that with this MacGyver model that you just saw. But what we did after the initial ideation is now looking at the form fit function. So if you look at older versions of the bellows, the one with the with the leather, it's almost gone down by 3/4 of its original size. It's shrunk significantly. If you saw the one with the long PVC pipe and the plunger, we've turned it into this double action piston system, which is one way of trying to miniaturize it. So the answer is yes. And if you look at new technologies out there for the variable PIP and stuff like that, they are not as big as.
Hello? We lost you a little bit. Hello? 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 Dr. Fresh?
Yes, sir.
Yeah, we lost you a little bit. Now you're back.
Okay, so can you hear me?
Yeah, you are loud and clear now.
Okay, so I think my concluding part was basically that we should be able to design this to the level that parents can carry them just like they carry feeding bottles. And you know, one of the common illnesses for kids when I was growing up was this sudden death syndrome that I always thought was heat stroke for babies. You know, when they tie you up in the back in that cloth and it's 90 out there and they walk you 10 miles, it's a very uncomfortable place to be. It's definitely not an oxygen chamber.
Yeah.
So can we design this, miniaturize this to the level that a mother can just turn around and put one on the baby and then, you know, ventilate them as they walk all these miles. So all those options are on the table.
Yeah, just like with the way we have the nebulizers, you know, for those who are asthmatic. So we can actually get something like this. I have a nebulizer for my kid at home that if he's, you know, is having these attacks, we are able to use that. And it has been working quite well. So if we get ventilators like that, you know, where, you know, it can assist people, especially the elderly, it will be very, very good. Mm-hmm. Okay, any more questions?
Yeah, and also we can think about these in, you know, most of these rural areas, you know, where there's no electricity.
Yeah, the mechanical one.
Yeah, you can come out with a hand pump. You know, somebody once asked me, I mean, how long is it going to take somebody to really pump this? You know, like the double piston one, just pushing it up and down and getting there. And I said, well, if you've lived in the village before, you have 10 people lined up pumping this in turns. When it comes to saving life in Africa, we are experts in that, you know. So I think all those possibilities are there. We can look at solar configurations.
Yeah. You don't lack labor when it comes to
wires.
those things.
Yeah.
Right. Any more questions? And then we can wrap up. And then in the absence of any more questions, we can be wrapping up. Thank you very, very much, Dr. Fred. Eugene, do you still want to ask a question? No.
Oh, it was just a little add up to, so you can also look at a situation where the miniaturized one gets affordable to an extent that, people can start to add it, carry it in their first aid, boxes, so that in situations where you want to administer a CPR, and in this COVID-19 era, you don't want to start to, put your mouth over somebody else's mouth when you don't know what is there. So, I mean, that's something for consideration.
Yeah, very, very good.
I think that's the oldest form of ventilator that was invented,
Yeah.
Right. Good.
Yeah. So no, those are good ideas. I'll be happy to reach out to you and we can have some more conversation.
Yeah.
Thank you.
This project for us is an open house. We invite people from all walks of life who want to become part of the academic city innovation ecosystem. It doesn't matter where you are. Like I said, we have folks in Austin, Texas, who join online on Zoom, making contributions. If you have expertise in ventilators, electronic systems, and you want to work with us, we are open. If you have your wards, your brothers and cousins that you want to give a world-class engineering education to, where else can you send them at this time? When everybody fled into hiding, Academic City stood up. And so that should tell you that they can get good quality education here.
Good, please. And you mentioned students, and you mentioned Academic City, of course, and you're talking about innovation. And can you tell us a bit about what you're doing now at Academic City so that we all know how you manage to get some of these students, second-year students, to be able to support you on this project?
Yeah. So, what is interesting about the Academic City experiment is that we have people that have actually worked in industry. So I came in with 16 years industrial experience. I've never claimed any academic titles. I came from a background where you get paid for what you deliver on. There's no storytelling. It either works or it doesn't. And so what I've been trying to do is to create an ecosystem of like-minded people who are doers. We are guided by 4 key pillars. That whatever we do has to be contextual for Africa. By that, we don't teach you everything that is in the book. We don't have a Greek engineering, but we send our kids into the farms to find opportunities to innovate. We are here to solve Africa's problems. And if you can solve, this part of the world has the most complex problems to be solved. In every area you touch, there's a problem to be solved. So it has to be contextual. It has to be experiential. You have to experience it. You have to go into the lab and build stuff. You have to touch stuff. We have, our third pillar is extensional, which we basically say, look, what we offer you here is a toolkit. We can't teach you everything, but we'll give you a toolkit so that you can go out there and seize the world, literally. And the one that I think is unique is what we call unified learning. And our unified learning model basically puts teams of students together across disciplines. So at the end of every semester, we have cross-disciplinary team or transdisciplinary teams working together on a project, each bringing their discipline's perspective to it. After all, that's how the real world works. The real world, engineer doesn't go off and do stuff on their own. The marketing person doesn't go off and do stuff on their own. They have to work together seamlessly in order to deliver a successful product or process. So those are the pillars that underline what we do here at Academic City College. And we are seeing students who in their second year are fearlessly standing, male or female, standing up to build stuff, to touch stuff in a caring environment, in an environment where there are no boundaries, in an environment where the president of the university is in the workshop with the students, filing stuff, building stuff, giving feedback, coaching and mentoring in a very hands-on way. And I mean, I think that speaks in itself a lot for our part of the world, where it's much more comfortable to give instruction from a distance and just pray and hope that things come out on the other end. So that is the kind of environment that we are creating here. We have small class sizes. Everybody gets to present, everybody gets to talk, everybody gets to be pushed out of their comfort zone, you know. And just to end that, you know, a parent came up to me last admissions cycle and he said, I really want my son to come here. And I said, why? And he said, you know, I secured a school for him in Germany, but I would prefer that he's here because he doesn't mingle well. His social skills are very limited. And if he goes far away, I don't know what is going to happen. So about 2 months ago, I had a parents' night and the father shows up again. And I said, hi, it's Nanaya. And he said, Nanaya has gone through a 180-degree transformation. I said, what do you mean? He said, before he came here, when I asked to take a walk with him, let's go do boy stuff, he doesn't want to do anything with me. Friends never come to the house. And now he speaks well. He goes out with me. He's engaged. That is transformational. And that is what we want to do for this new Africa. A transformational Africa where when your kid comes home after the first semester, you can actually see changes in them. And that is what we are driving. And we are succeeding because these kids that took part in this project, they volunteered. I didn't tell them they must come in this curfew and come and work on this project. They volunteered, and the fact that they did is quite interesting. One of my old students from Ashesi University volunteered to come as well. So what that tells me is that we are making an impact, because if your old student, long after you are gone, is still willing to come and work with you on projects, you know, it's a sign that the changes that we want to see in Africa is beginning to happen in real time.
Great, great, really. I really like this. And I think we need to encourage more universities to get into this space and begin to transform the way teaching and learning is done in this part of the world. Thank you very much once again, Dr. Fred Magbaganlori, President of Academic City University College, and also our board chair of the Institute of ICT Professionals Ghana. We thank you for your time. We thank all participants for joining us today. I know it's midday, most of you are at work, but you managed to log in. We got about 35 to 40 people coming on board. And it's been a very exciting webinar. The video for this webinar will be available. We'll post it on our YouTube link. We'll share the YouTube link via email also. So those who are not able to follow everything through can also get opportunity to play back. Thank you very much. This is the beginning of good things to come, and I look forward to more innovations in the future. Thank you.
Thank you. Thank you very much. Have a good day, guys.
Good day.